So today we're going to be talking about section 1.5. Is everybody here? Then there's like 2 more people who are going to be filing in. Go.
Unless they're online.
Yeah. So section 1.5. This is when we start getting into the meat of the class. This is where what section 1.5 is about are these things called limits. And if you had to guess, just from the name of it, what do you think a limit is?
Where it stops, where it can go.
In a sense, yeah, actually, yeah. That's a great way of describing it. What about y'all at home? What do y'all think a limit is?
Kind of like a barrier.
Kind of like a barrier, in a sense, yeah. One way to think of a limit is if we could get to this number x, based on the things around x, around this one value, what would our function be? So instead of saying, what is our function at x, right? So instead of saying f1 is equal to, in this case, 2. It's saying if we could get close to 1, based on those numbers, what do we think 1 would be? Does this make sense to everybody? Kind of, sort of? Good, it shouldn't get. What it's really getting at, and the next slide shows really well, is exactly what I mean about based on what's around it. So we've got 1 here at our table, right? But we're not looking directly at 1. We're going to look to the left of 1, to the right of 1. We're going to say, based on those numbers, what do we think our function would be at 1? Now, having said that, notice we're talking about it coming from the right. We're talking about it coming from the left. This is going to be important to us in a little while. But really, it's just about this thought here. Let's say 1 is right here. So let's say our function looks something like this. Based on what we've got, this is where 1 would be. But we're going to look at these values. We're going to say, all right, let's look at this group of values immediately to the left of 1. In our case, they're associated with these values, right? Which show up over here in 1. And then over here, same idea, except they're associated with these values up here. What we're going to do is we're going to say, as each of these little bubbles gets smaller and closer to 1, what do we think happens?
So this kind of be, I don't know, to bring it more into perspective, but this kind of work like a car part. You can't put a bigger nozzle into a smaller one. It has a variancy.
Kind of. It's more like this. So for those of y'all at home who might not be able to see what I'm doing, I'm going to walk across the room, but in half steps, right? So I get halfway across. I get halfway across again. I get halfway across again. I'll never actually reach the wall though, right? Like I'll never fully get to that other side. But we understand the limit of where I'm approaching. The thing I'm getting closest to is going to be the wall. That's what we're doing with limits. We're saying we're going to take X values inside of these bubbles. We're going to shrink our bubbles, so our X values have to get closer to 1. When we do that, what does our function do? What does it get close to? And does it depend on the direction, right? Because we can think of other graphs, like for example, a graph like this. Coming from the right, we're going to get close to this y value, right? But coming from the left, we're going to get close to this y value. So this idea of the limit, it's going to have something to do with our style of function. It's going to tell us something about the behavior of our function around particular points. Everybody cool with this? Yep. Cool. Having said that, one way to address the question of what is the limit is to use a table like this. So in our original question, we're asked, what is the limit as x approaches 1 of the function x squared plus 1? We're like, okay, well, I know I can plug in 1, but that's not what the limit's asking. The limit's asking everything else, right? It's asking this idea of what it's getting close to around. So we start, before we actually understand all of our methods yet, we'll start by using tables. We'll say, all right, we're going to use 1 in our table, but it's just a reference value. We want to look at all of the values to the left and to the right. And using that, we can say that our limit from the left and from the right approaches 2. Now look at this idea here. What they're trying to say is exactly what I just said with these bubbles, right? They're just showing it with the arrows. Because as we shrink up here and up here, we shrink down here and down here. Yeah? Is everybody cool with this?
I think part of the question would be is why would the parabola, like the bottom part, be shrinking if it's literally on the same variancy line?
All right, so think of it like this. So what I'm saying here isn't 110% just yet. This is just to get us going first. Okay.
So, no, I'm not asking about the problem, because you said it moves up or it goes down based on where it's coming from. My question is, even if it does go up and down the line, why wouldn't it stay on the variancy line and just show you more, rather than moving the parabola bottom?
Ah, I got you. So what's functionally happening here, or at least I think I've got you. What's functionally happening here, say what?
I said if not, I'll just keep asking in a different way.
Hey, that's all right. If that's what it takes, that's what it takes. I am here to facilitate learning. That means I'm willing to do whatever it takes to help you all learn. Okay. So one way we can think of this is to say, let's imagine we start off with these bubbles, right? These groupings of possible X values. Now let's shrink them. Let's hold this idea, right? That on the left, we're going to be from A to 1, but not including 1. And on the right, we're going to be from 1, but not including 1, B. Now let's let A get close to 1. Let's let it shrink in a little bit. So that now it looks like this. When we do that, this bubble shrinks, right? And when we do that again, we get even closer. So all the possible y values shrink in. They approach the solution. Does that help explain a little bit?
Kind of, not really, because like, I guess it's not gonna be clear, I guess, because I don't understand why the curve would move up and down, but that's, I guess that's just something I'm gonna have to figure out. Because you explained it, it's more clear, but I don't know. I don't know how to ask it in a different way.
That's fair. This might be something that I'll have to answer after class. Now, like I said, this isn't 110% correct in the way I'm addressing it just yet, because I'm saying we're shrinking X and we're getting Y. The way the proofs work, it's actually the exact opposite. It's backwards. We're going to shrink Y to get X. But again, I'll explain more of that later. But right now, what we need is an intuitive, conceptual understanding of what this is. We're just saying, as we get close to 1 from either direction, what's going to happen and why. So, again, showing all of this together, there's 2 different ways of thinking about this. We can think of it tabularly, or we can think of it graphically. This graphic is just saying, check it out, we're getting close to this point as we move from the left and as we move from the right. Having said that, what do y'all think the limits will be as X approaches 1 for either of these?
Would it be on the negative side?
Wouldn't it be on the negative side?
Because you're dividing -1.
Well, not quite, right? Because we're getting close to X is equal to 1, right? So what happens when X is equal to 1? Just out of curiosity. It doesn't exist, right? But if it could exist, if we could make it exist, what would happen here? So let's think of it this way. Our graph looks something like this. There's a hole right here. And this hole occurs when X is equal to 1, Y is equal to 2. So when we take the limit as X approaches 1, we should expect to get 2 out, right? Because look what happens when we get close to 1. When we get close to 1 over here on the left, we're getting close to Y is equal to 2. And when we get close to 1 from the right, again, we get close to Y is equal to 2. But we can't put in 1 to verify this. So to look at this graphically or numerically, in the graphical case, we're approaching this point, Y is equal to 2, right? And if we were to look at it tabularly, check out what happens in our table. Coming from the right, we get close to 2, but we'll never quite reach 2. Coming from the left, we'll get close to 2, but we'll never quite reach 2. So this whole idea is to say, Well, I can't put in 1 into this equation. Doesn't work. Because there's a hole there. But if I could put in 1, what would I get? Everybody cool with this? So another way of saying this is 1's not in our domain. But if it was, what would happen? Get what I mean in that way? Yeah. Having said that, there's this other example, right? This absolute value of x minus 1 divided by x minus 1. Graphically, that's going to look like this. Check it out. We've got these open circles here, right? That means that neither one of them actually exists at that point. Does this make sense what I mean? This is the graphical equivalent to saying a rounded bracket. Whenever you see an open circle like that, you're graphically saying this. Whenever you see a closed circle, you're saying something like that. Is everybody cool with this? So graphically up here, we're saying I can't get to 1. That's not possible. But coming from the left, coming from the right, we're getting close to 1. Coming from the left, we're getting close to -1. Notice our limits don't agree from the left and from the right. So what this tells us is the limit does not exist, because there's not an agreement. It's like we have to have 2 parts of our equation or function saying the same thing in order for this limit to exist. Is everybody cool with that? All right, so I know it's Wednesday morning, but everybody cool with that? Yeah? Awesome. So looking at this tabularly, we can see that again. Coming at it from the left, we're getting close to -1. This decimal actually expands out for a little while longer. Coming at it from the right, same thing, except it's 1. So they're not in agreement. And in this case, we would say that the limit as x approaches 1 of the absolute value of the quantity x minus 1 divided by x minus 1 does not exist. E. The reason why is because from the left and the right, we don't agree. If we agreed, we would say it does exist. So, some takeaways here. First, saying that the limit of x, of f of x approaches L as x approaches C means we're getting close to L as x gets close to C. Right? So we're saying what's in the neighborhood, in a sense. In order for a limit to exist, then coming from the left and coming from the right, we have to have an agreement. We have to be able to say the limit from the left is equal to L, and the limit from the right is equal to L. If we don't have that, the limit does not exist.
So if you get 2 different numbers, then it just doesn't exist?
Yeah.
Okay.
And we'll expand on this a little bit more in just a second, but yes.
So like that graph where it had like the two separate dots, that's when you know you're just like.
Exactly.
Okay.
In the case that a limit doesn't exist, we have what are called jump discontinuities. This is a jump discontinuity. When your graph is totally just broken, right? It's not like there's a hole here. No, there's a gap, a chasm, a Grand Canyon of numbers that you can't jump between. Because how do we decide? If I'm coming from the left and I get to 1, and I'm coming from the right and I get to 1, and I'm coming from the left and I get to -1, how am I going to decide what my limit is? They don't agree in directions, right? There's a chasm of numbers, a Grand Canyon of numbers that exist from 1 to -1. And I gotta choose between one of those? No. I just say it doesn't exist. Right. So this last point is getting at something particular. Getting at, I'm going to just draw this as an example, because I don't think I have a graphical example. Oh, I do. Okay. I'm not going to draw it. This example here. Notice we can plug in 1 into our function. When we do, we'll get 0. That's this point way down here. That equation was this right here. Our function is equal to x whenever x isn't equal to 1, and it's 0 when x is equal to 1. So all we're saying is, when you get to 1, instead of spitting out a 1, spit out 0. So we can put 1 into our function, but when we do, it doesn't agree with the limit. So the limit isn't asking what our function is at the point. The limit is asking, based on the numbers around our point, what would we guess the function is? Make sense? So here, the limit would give us 1, but the function, just by itself, f of 1 would give us 0. So what I'm saying is that in this particular case, example. So our limit doesn't have to be equal to what our function is equal to. Everybody cool with it? And again, think about it. We're talking about what we're getting close to in our y value. That's what the limit asks. It doesn't ask what your function is at x. It asks, as you get close to x, what does your function get close to? Make sense? Yeah. How about y'all at home? Does this make sense so far?
I'm a little confused. Can you explain it again?
Which part in particular is confusing to you?
Almost all of it about this last example.
Yeah, no, this is all confusing, I will admit. So let me draw up these 3 different examples that we have. First one was this case. This was x minus 1, the absolute value, divided by x minus 1. Second case No, my bad, this was x squared. This one was the x minus 1. And then this example here. All right, so what we've got up here on the board is all three examples side by side by side. In this example, the limit's going to be 1. And the limit's going to be 1 because as we get close to x equal to 1, this gets close to 1, right? Like everything up here gets close to 1. Cool with that? So the question that was asked here was, we call that h of x. This limit came out to be 1, but h of 1 came out to be 0. This limit, let's call this g of x. This limit, as x approaches 1, does not exist. And interestingly enough, throwing in 1, our function doesn't exist either. In this case, as x approaches 1, our limit comes out to be 2, but our function evaluated at 1 does not exist. So what we're doing is saying, as we get close to this x value, all of our limits here were 1, right, as x approaches 1. So in each of these, as x approaches 1, in this case, our function approached 1, even though our function wasn't 1 when x is 1. Make sense what I mean? Does that clarify it a little bit?
Yeah, thank you.
Awesome. Cool. So, having said that, the definition of the limit of the function is as follows. We say that our function f approaches L as x approaches C. Right? This is just the first little bit of how we even state or read what this limit is talking about. This is the limit of f of x as x approaches C is L. And what it's really saying is we get arbitrarily close to L as x gets arbitrarily close to C. That's all that means. So one way to think of this is the limit is algebra in motion. We're literally moving our numbers. We're saying we can pick any number that gets arbitrarily close to 1. And if we choose them from one direction, if we choose them from another direction, and it agrees in what f approaches, then the limit exists. Is everybody cool with this? Having said that, there are a couple properties. The limit of a constant is just going to be that constant. The limit of x, as x approaches c, is just going to be c. That makes sense, right? Like, as we get arbitrarily close to c, x is just going to approach c. Yes, ma'am?
What slide is this?
I'm sorry, what was it?
What slide is this? If you, sorry, if this is-
This is slide 40. X to the nth power, as x approaches c, is going to approach c to the nth power. The root, similarly. But notice we have conditions on whether n is even or odd, right? So jumping ahead to that next slide, just some operations with limits, right? If we multiply by a constant, we say some constant k or b times our function, and then apply the limit to it, our answer is going to be b times whatever the limit of our function is. Cool with that? Similarly, addition and subtraction. Here we're going to say the limit of f of x plus or minus the limit of g of x. It's going to be whatever those limits are, added or subtracted. Similarly, multiplication, division, assuming that k doesn't approach 0 with division. If we take a function and raise it to a power, the solution is going to be the limit of that function raised to that power. Same thing with the root. Everybody cool with that? So, as another example, the limit of as x approaches 2 of this polynomial. Based on those previous rules, one of the first things we can do is break up our polynomial into 3 different limit questions, right? We said the limit as x approaches 2 of x squared, of 2x, and of 3. But we keep those in-between operations the same, right? We keep the addition and we keep the subtraction the same. We evaluate each of those limits independent of each other. And then we do those final operations, that addition and that subtraction. So what is this really saying? We have these tiny smaller functions that make up our polynomial. The limit, when you have the addition and subtraction of 2 different functions, is equal to the limit on function 1 plus or minus the limit on function 2. Cool with that? So, having said that, I'm trying to think of how I want to say this. I know how I want to say this. I'm going to show this with this first example here, actually. What this is saying is that if you have two functions that are identical everywhere but at C. So we want, in our case, the limit as of f of x as x approaches 1. But in our case, let's create another function. Our other function is going to be g of x is equal to x plus 1. Well, looking at this, g of x and f of x, they're identical everywhere except for at 1, right? So f of x is equal to g of x when x is not equal to 1. So to solve this, one thing we could do is use this function instead. So this tells us that the limit as x approaches 1 of f of x is equal to the limit as x approaches 1 of g of x. And in our case, the limit's going to be the same thing as just plugging in 1 for x. So this substitution sort of method, this replacement theorem, actually makes it easier to solve these. Now let's stop and think about this for a second. Why would this be the case? Why would we be able to substitute one function in for the other? What do you all think? Well, let's think about what the limit's asking, right? It's asking what happens when you get close to 1 here. Well, if it's identical everywhere except for at x is equal to 1, the same thing's going to happen over here, isn't it? Like as we get close to 1 over here, which would be, let's say, right here. As we get close to 1, all the same things are going to happen. So the limits are going to be equivalent in that sense. But the functions themselves are not equal. Does that make sense for me? Kind of, sort of? No? Okay. So we're going to delete this point, right? We're going to omit it entirely. Just ignore it. As we get close to 1, we can kind of get an idea of what this is, right? Now, we're going to do the same thing over here. Because these functions are identical everywhere except at that one point where x is equal to 1. Removing this, ignoring this for a moment, and looking all around it, we're going to get the same values, right? Agreed? And because we're getting the same values, we can go ahead and say, let's ignore our first function. Let's work with this one instead, because this one's a little bit easier. So it's about the behavior of your equation around x is equal to 1. And as long as that behavior is preserved everywhere, except for at that one point, then you're good. Everything's going to come out the same. Make sense what I mean? Kind of, sort of? Is that, I don't know. Okay, think of another way to explain it. I know. Let's think about what we've done here. How did I know that this is going to be x plus 1? What did I do?
Simplify the other equation.
Yes, that is all I did. I said, check it out. We've got x squared minus 1 over x minus 1. Well, this is the same as saying x plus 1 times x minus 1 divided by x minus 1. We can simplify this and we get x plus 1. But when we do, we've gotten rid of a discontinuity. Because check it out, this thing, it doesn't exist when x is equal to 1, right? Because we got a 0 in our denominator. But this thing exists everywhere. So we would say that our equation, when simplified, is equal to x plus 1 everywhere except for when x is equal to 1. And because it's equal everywhere except for when x is equal to 1, if we were to take a table of values for this equation, the table of values for this equation, they come out to be identical except for that one spot, right? And in that way, the table of solutions, the table of those points, they're going to be identical. So whatever this limit approaches, this should also approach, right? Because that's what we started with. Was this tabular sort of approach, right? Cool. So let's jump to the next part. So I'm going to let y'all play with this for a second. I'll give y'all like 2 minutes. See if you can solve this on your own. So this one's going to take some time, right? Like this x cubed minus 1, how the hell does it factor? Like what statistic ass would put this as a question to anybody? So, having said that, this is part of the reason why I made those algebra review notes available to y'all. Because things like this, if it doesn't jump out at you right away, probably is a good sign to go back and look at those review notes, right? Because what we're doing here is factoring in this one, if you don't know all of your factor methods, it's going to take a little bit of time. Having said that, jumping to the next slide to give you all an idea of what's going to happen here.
So when you're factoring out, it would end up being x plus 1, x minus 1, like in the parentheses, x plus 1, parentheses, x minus 1, parentheses, x plus 1. And then you just cancel out the x minus 1 and then it just be squared, x squared.
I think
1.
so.
So then it would end up just being a complete.
A parabola?
Yeah.
Yeah, it should end up being a parabola. Without saying it written on paper, it's like holding all of that in my head right now is a little rough. But we can see from looking at the graph of it, right, that it is in fact a parabola. You're absolutely right. Just a parabola with a hole missing, with a spot missing. So this automatically tips you off to what you're saying probably being correct, or at least on the right track. So when we factor it all out, what we're gonna get is x minus 1 times this polynomial x squared plus x plus 1, which I think is what you said, correct? One way we could have approached this is to have used long division. I personally think that would have been a lot quicker. I think that would have been like not real. And this is why I wanted to give you all some time to look at this problem, just to kind of motivate you all to look back at these different factoring methods. But we can see though, looking at this, when we factor all of this out, what we start off with has a discontinuity when x is equal to 1, because we can't put that in. Our denominator turns to 0. So we can't put in x is equal to 1. But once we simplified everything, we got out a polynomial that doesn't have this discontinuity. So these two things must be equal everywhere except when x is equal to 1. Having said that, I'll talk about that later. So what we've effectively done is we plugged the hole. We become that little Dutch boy with his finger in the dam holding the water back, right? Plug that point. And by doing this, we can now say, hey, I have a function I can actually evaluate at this this continuity. And because I can evaluate my function at this discontinuity, I plug this hole, and it's not a jump discontinuity, well then I can go ahead and just plug in C, or in this case, 1. And the reason why we can just go ahead and plug in 1 now, because it's not a jump discontinuity. Is everybody cool with that? Yep.
So plug it back into the polynomial and it comes out as 3, then it's nowhere at a limit?
No, so what I'm saying is, in this particular case, what we've done is plugged the hole in a continuous function. And by doing that, we've said, all right, cool. Now we can go ahead and just evaluate our function as if the limit wasn't even there.
Okay,
Does that make sense what I mean?
Find where the limit is.
Right.
Okay.
Right. So now we can,
Don't die.
I'm trying not to. Y'all saw that, right? The table attacked me. All right, dad joke. I know, I'm sorry. Anyhow, what I'm saying is, we were saying, all right, as we get close to this point, and as we get close to this point, that's like saying, as we get close from this direction and as we get close from that direction. And because this is getting filled, we can just go ahead and use this new solution. We can just go ahead and plug in 1 here into our new function. Make sense? So this is only because all we've done is filled the hole when it's not a jump discontinuity.
So like, say we're putting this into our homework, factored into the polynomial, and we found that it's like at 1, it's the y is 3. Is that what we're gonna put in for the answer, or are
For
we gonna
web
put in?
assign, it should just be the actual value. It should just be 3.
Okay, so we go.
Yeah, so what else I would expect,
I didn't know what the.
just that. Having said that, I do want you all to do this by hand anyhow, right? Like, yeah, it is web assigned. And yes, you have all of your online tools that will solve some of these problems for you. Do it by hand anyhow. There's, the point of all of this is to learn it, right? And the point to learn it isn't necessarily because the biggest reason to learn all of this is because it teaches you a new way to think. It teaches you mathematical thinking, which is kind of this idea of, based on what I know, what step can I take first? Okay, based on what I know now, what next step can I take, and so forth and so on. It's this iterative, stepwise thinking process, right? And if you sit in this class and don't do any of the work by hand, you just plug it into your online platforms, get out these solutions, you're not learning that thinking process. And that's what your employer wants you to have at the end of the day, right? It's this sort of mathematical thinking process. It's not so much necessarily that you're going to use all of these tools. So be honest, some of these tools you're not going to use. Some of them you will, a lot of them you will, but not all of them. So the biggest thing you gain from this class is the mathematical thinking. You only gain it if you actually do this all by hand. Just normally a talk I give that first day of class, but well, we all know how that went. Having said that, let's keep going. Say what? Damn. All right. Yeah, it is time. All right. Have a good rest of your day, everybody. I'll stick around if anyone has any other questions.